As always, please pause the video to examine the question before moving on. In this question, we are asked to calculate f prime of a. Now, f prime of a is simply the derivative of the given function at any number a. Let's take a look at the formal definition of f prime of a. In other questions, we would try to understand the origin of this expression, but for this question, we will take it for granted for now. We're going to use this expression to calculate f prime of a of the given function. Now, when we go to compute f of a plus h, that simply means we're going to take the expression a plus h and plug it in wherever we see an x in our function. So we'll go ahead and plug in a plus h wherever we see an x in the given function. Similarly, to compute f of a, we will simply plug a into any x that is present in our function. And then we'll put that entire result all over h. And to continue, we might consider multiplying the 3 using the distributive property to each term in the parentheses. And we end up with an expression that looks like this, a limit, I should say. And this is a rather complicated limit to evaluate. Notice we can't simply plug 0 in for h because doing so would place 0 in the denominator, which would cause the expression to be undefined. So we have to use some mathematical ingenuity to proceed. Now, that mathematical ingenuity involves multiplying the numerator and the denominator of the expression by something called the conjugate. Now, basically what that means is we're going to multiply the numerator and the denominator by this whole term, but we have to make sure that we change the sign. So in this case, because it's subtraction, we're going to change that to addition. Again, please note that we changed the subtraction sign to an addition sign. So now we're going to have to go ahead and multiply this, and we're going to basically use the method the method of foiling. So we're going to multiply the first terms, followed by the outside, the inside, and then the last. And here's what the numerator would look like after that. The result probably looks rather complicated, but we can see that this complicated term that has two radicals has a positive version, and it also has a negative version. So it turns out that those actually will cancel out conveniently, and that's only going to leave us with this first block of terms and that last block of terms. Notice also we included a parenthesis around that last block of terms because we're going to have to distribute the minus sign to each term. Now, after distributing that minus sign and canceling away those large complex terms, we're left with the following expression in the numerator. If we look carefully, we can see that the positive 3a and the minus 3a cancel, as well as the positive 1 and the minus 1. Additionally, we can see that after simplifying the numerator, the h in the numerator and the h in the denominator are going to cancel away as well. So the limit continues to get simpler and simpler as we proceed. And at this point, since we canceled the h out of the denominator, we're going to finally be able to plug 0 in for h. We couldn't do it previously because that would have placed 0 in the denominator and made the limit undefined. But now that h has been canceled away, we can go ahead and plug 0 in for h. Here's what the expression looks like after doing so. Again, we've plugged 0 in for h right there. The denominator is going to include two terms that are both 3a plus 1, because 0 plus 1 here is going to make 1. So we're going to have two terms that have the square root of 3a plus 1. And when we combine those together, it would look like the following. And that is indeed the correct answer.